Gravitation. In the universal law of gravitation, Newton said that the force, the force of gravity which exists between the two objects is directly proportional to the product of the masses. It's quite obvious that it will be directly proportional to the product of the masses. But there was one surprising factor, and that was he said that force of gravity between the two objects will be inversely proportional to square of the distance between the two. If there are two bodies like A and B and they are separated by the distance R, now what was the reason that why he said that force of gravity which exists between the two object is inversely proportional to the square of the distance between the two? What was the reason? How he reached to this conclusion? He reached to this conclusion by exploring the third law of Kepler's planetary motion. Like Kepler has said that each and every planet moves around the sun in an elliptical orbit. uh, Newton said that instead of that it is moving along a elliptical orbit, let's consider that it is a perfect circle, so that the radius, the value of the radius r1, that is the value of the distance between the sun and planet, is constant all the time. Wherever from you look, the distance is constant. Which distance? That is this distance that represents the radius. Okay. So he said that let if it is undergoing a motion, let it is moving because it's moving in a perfect circle. So and it is moving with the constant velocity v, right? Because it is moving in a sphere, it is moving around a circular path, so its velocity will not be affected by the gravitational force because there is equal distance anywhere. If we look between the planet and the sun, it's equal. If we look at the position p1, position p2, position p3, the distance between the sun and the planet is same every time, everywhere. So its velocity will remain constant. Gravitation will have no, you can say, no rule here. Although it will move around the sun with a constant velocity, right? But somewhere, what we have seen in case of Kepler's, we have seen that as the distance between the sun and the planet decreases, the velocity increases because of the increased gravitational force. And as this distance between the sun and the planet increases, the gravitational force decreases. Like we have seen in case of Kepler, when he said that the planets move around the sun in an elliptical orbit, and sun being at one of the foci, if the distance between the sun and planet is very less, so gravitational force will be more and there will be speed will be more. But as the distance between the sun and the planet will increase, the gravitational force will decrease, and because of that the speed of the sun will be less. But here nothing as such happens. Why? Because it is moving in a perfect circle, right? So it's moving with the constant velocity v, and let t be the time taken by the planet to move from position A and to complete one revolution and reach back to point number A, right? So the force existing, the centripetal force which exists between the two objects, that is between this planet and the sun, is directly proportional to square of the velocity upon radius, upon the distance, right? When a planet moves with a velocity v in a circular orbit of radius r, the force acting on an orbital planet, the force which is acting on this planet, is directly proportional to v square upon r, right? But now how to find out this v? How to find out the velocity? You know, velocity is equal to distance traveled upon time taken. You know about it, that velocity is s upon t. Now, how can, what's being the circular path, the s, how can you calculate the circumference of the circle? That is calculated by 2 pi r upon t. Let t be the time taken by the planet to move around the sun, right, from point A to point B. Okay, but you know, this R will change for this, the value of this R will have different value for different planets. Why? Because every planet has its own orbit. Every planet has its own orbit. So this R will change as per the planet. Even the time taken by the planet to move around the sun will not be the constant for all the planets if we are talking about, right? Now, okay, just a moment, let me, okay, but 2 pi will be constant. 2 pi will be constant. Once we scrape this 2 pi, once we remove this 2 pi, the sign of equality will change into proportionality. So we can say that V is directly proportional to R upon T. V is directly proportional to R upon T. Am I right? Once you, because 2 pi is a constant, in order to remove the sign of proportionality, we always introduce a constant. Once you remove the constant, it will, what it will tend to do, it will, the equivalent sign will be changed into proportionality. Now squaring both the sides. So we will get V square is directly proportional to, let me write it here. Squaring both the sides, squaring both the sides, we will get V square is directly proportional to R square upon T square. R square upon T square. Now multiply by R as well as divide by R on left side. So what our equation will look like? It will be R cube upon T square. R cube upon T square into R, right? R cube upon T square into R. But according to Kepler's law, this R cube upon T square, according to Kepler's third law, the R cube upon T square is constant. The value of this is constant. So we can say V is square is directly proportional to 1 upon R. 1 upon R. Right? Now, substitute the value of V square in the equation number 1, that is where the value of F is directly proportional to V square upon R, right? V square upon R, this was the first equation. Now substitute the value of V square in this equation. So we will get F is directly proportional to 1 upon R and 1 upon R. In mathematics, when bases are same, powers are added. So I can say F is directly proportional to 1 upon R square. This is inverse square rule. This is what we know as inverse square rule, which was used by Newton in postulating his famous universal law of gravitation, right? This I hope now. So, according to Newton's second and third law, according to Newton's third law, uh, every object in this universe attract every another object with a gravitational force that is directly proportional to the product of the masses and inversely proportional to the square of the distance between the two. This is what the universal law of gravitation, which was proposed by Newton, say. Now Newton has given us one more law, and that was Newton's third law of motion, in which he said that each and every object will be will be just they will they to an equal if the two objects act upon each other, they will exert in equal and opposite forces on each other. That is what the Newton's third law of motion says, that both the object, once they act over each other, they apply the force. The forces will be equal, right? The forces will be equal but opposite. Therefore, now we can say that universal law of gravitation also says that the force is existing between the two objects. Now, please look at this pen. According to Newton's third law of motion, if this if Earth is exerting a force on the pen, then pen should also exert an equal amount of force on the Earth. Right? This is what third law says. Right? And you know that as per the Newton's universal law of gravitation, force will exist between the two objects. As per the universal law of gravitation, the gravitational force will act between the two objects. Then once I release the pen, why is it that we see the motion only in the pen if as per the Newton's third law, if they are exerting an equal force on each other? The question is this, that if the force is existing as per universal law of gravitation, force exists between any two objects, let the two objects be Earth and this pen which I am talking about, right? As per Newton's third law, the force will be equal. That means that whatever force is exerted by the Earth on the pen, an equal amount of force is exerted by the pen on the Earth. Now, once I release this pen, why is it that we see only motion in the pen and not Earth moving towards the pen if the forces are equal? There is some fundamental problem with the third law then, isn't it? Don't you think so? That there is some fundamental problem if in Newton's third law of motion, Newton say, let this be sun and this be Earth. Or let's see, we have not seen the sun and we have not seen the let's take a day-to-day example. This is Earth and this is the pen which I was holding on the surface of the Earth. There exists the gravitational force between the two, right? And now as if the force exists between the two, as per the Newton's third law, the force should be equal. If Earth is exerting a force on the pen, so an equal amount of force will be exerted by the pen on the Earth. Then why is it that once I release this pen, we see motion only in the pen. Why Earth is not coming towards it? Because if due to gravitational force, it comes in motion. Due to the gravitational force, it falls towards the Earth. But as per Newton's third law, forces are equal. Then why Earth is not moving towards the pen? Why don't we see the motion towards the Earth? Right? Now, this is your question. Please answer me for that. Okay, so let me explain it to you that why we see the pen falling towards the Earth. But why Earth is not jumping towards the pen? If I am allowing this pen to fall and it is falling towards the Earth, why Earth is not jumping towards the pen? We can explain it because there might be some fundamental problem in the Newton's third law as per our understanding. But no, there is no fundamental, nothing wrong with any of the two laws. Nothing is wrong with the universal law of gravitation and nothing is wrong with the, yes, now we will be explaining that why we see that pen is moving towards the Earth, this duster is moving towards the Earth, why we see every object when allowed to fall from a height falling towards the Earth. Even if we allow the jet plane to fall from a particular height, it will fall towards the Earth and you will never see that Earth will jump towards, although mass of the jet plane is large. Even if we allow a tank, which is a quite big, which have a huge mass, if we allow a battle tank to fall from a particular height, you will see that battle tank is also falling towards the Earth and Earth is not jumping towards their battle tank. Now, what is the reason why? You know, according to Newton's second law of motion, force is equal to mass into acceleration. That's what the second law says. Now, what will be the acceleration? Acceleration is equal to force upon mass, right? Acceleration is equal to force upon mass. So I can say that acceleration is inversely proportional to mass. In other words, we can say that acceleration is inversely proportional to mass. Acceleration produced in a body is inversely proportional to the mass. That means if mass is less, then what will happen to the acceleration? Acceleration will be more, and if mass is more, then the acceleration will be less. So now compare the two objects. One is Earth and one is this pen. Compare it. Compare their mass. It's quite big. It's quite big. The mass of Earth is quite big. So you cannot say that. So the acceleration produced as compared to this pen will be very, very negligible. So that's why we do not see Earth jumping towards pen. But comparing the mass of pen with the Earth's mass, it's very, very small, very, very less, even negligible, we can say. So that's why we can see that acceleration produced in the pen is more, as that's why the pen is falling towards the Earth. This is how we can explain, this is how the three laws are related. How the three laws of Newton's second law of motion, Newton's third law of motion, and universal law of gravitation, which was proposed by Newton, you can say they prove each other that they are quite right at their own places in their own zone, right?